Now we are going to discuss about CFSE, that is crystal field stabilization energy. Crystal field stabilization energy in octahedral complexes for various DN configurations. So before mentioning the crystal field stabilization energy, I would like to discuss about spectrochemical series. Of course, the spectrochemical series is not there in this particular topic, but without knowing this topic, it is not easy to understand this topic that much easily. So what is spectrochemical series? Arrangement of ligands based on their strength. This arrangement which we are showing here, right, that is going to give us a clear picture about which ligand is strong, which ligand is weak, and this is the result which came from the spectroscopic studies, and so this is called as spectrochemical series. This spectrochemical series, if you are clearly observing, halogens will come under weak ligands. Here you can see halogens, and here carbon attached nitrogen, carbon attached to oxygen or NO2 will come under strong field ligands, right, and nitrogen attached like amines and all will come under moderate ligands. So from here we can get a conclusion CNOX. The one which attached to the one which attached to carbon will come under strong ligand. The one which attached to nitrogen will come under next to the carbon, and then oxygen, and then halogen. This is the series of the ligands arranged in the arranged based on the strength. So who is strongest ligand here, which will give high splitting? CO. Best splitting will be given by CO, then Cn minus, then triphenyl phosphine, nitro group NO2 minus. Like that we will move on to ammonia, then move on to water, then move on to what to call so called halogen group elements. So based on this one, we will be able to understand which ligand can do high splitting, which ligand can do low splitting. What is the meaning of low splitting and high splitting? We already have seen in the previous topic, splitting of orbitals in different things, right. Now based on this ligands only we will discuss about this field splitting, and based on this ligands how we are going to discuss, one we will call it as low spin complexes. That means, for example, if you are considering Cn or NO2 or CO, if you are considering these complexes, these ligands, right, they will form low spin complex. What the meaning of low spin? So the splitting will happen, and the electrons will be filled first here. I am talking with respect to octahedral complex. Electrons will fill first here. If I am considering D4 configuration, 1, 2, 3 electrons will fill here, and fourth electron can enter here or here. If fourth electron is entering here, that is going to be called as low spin complex. When it is will be filled here, when the fourth electron will fill here, whenever the ligand is stronger. Just we have seen it, right, in spectrochemical series, same way. So same way this D4 configuration, whatever will be, not only D4, D5, D6, etc. D4 configuration, if I am writing in this format, splitting here and here, right, 1, 2, 3 electrons, filling 3 electrons are same in both. Now in case of high spin complex, example water, any halogens. So in this type of ligands, it will form a high spin complex. What is the meaning of high spin complex? The fourth electron will tend to move to higher energy level. It will not undergo pairing. Why? Because high spin complex delta naught is less than pairing energy. So electron will jump to the higher energy level. It won't undergo pairing. Whereas in the case of low spin complex, it undergoes pairing, and so it's called as low spin. Low spin. In spin is the spin. is undergoing low spin. High spin is in case of weak ligands. Low spin in case of strong ligands. These two topics must be known to find out the crystal field stabilization energy. Crystal field stabilization energy, to find out crystal field stabilization energy, we must know these two topics. And moving on to topic, what is this crystal field stabilization energy? First we have to know, right? Why? What is this crystal field stabilization energy? Without knowing how to calculate this one, rather than knowing calculating first, let us know what is CFSE, crystal field stabilization energy, right? It is crystal field stabilization energy is indicated with CFSE in a shorter form. It is the difference in the energy of the electronic configuration in the ligand field to the energy of the electronic configuration in the isotropic field. That means in the degenerate field and in the ligand field. For example, ligands are approaching metal ion. Ligands are approaching metal ion. Once after approaching, what happens? It will undergo splitting. What is the energy after splitting? What is the energy before splitting? The difference will give you CFSE. Again, we are discussing CFSE is the energy difference between electrons in the ligand field minus electrons in the isotropic field. Very simple. So, this isotropic field is all about pairing energy. How many electrons are paired? That is the information which you are going to get from the isotropic field. So, to calculate the CFSE, we must know ligand field, electrons in the ligand field and electrons in the degenerate field. If you are knowing both, right, we can calculate the CFSE. Right? Calculation of CFSE, we are now going to see now for different examples. Right? Now, I am going to discuss about CFSE with different examples. Example, FeCN6 4 minus FeH2O 6 2 plus. Both these complexes are octahedral complexes only, and I have taken here cyanide. Just now we have discussed this is a strong field ligand, strong field ligand, and moving on to here water. This is weak field ligand. So, I am going to take both. So, obviously we know that a strong field ligand will give which complex? Low spin complex. The weak ligand will give which complex? High spin complex. So, I am going to show the calculation of CFSE for both the examples, high spin complex. Now, moving on to FeCN6, here Fu is in +2 oxidation state. Here you can see x minus 6 is equal to minus 4, and so x is equal to +2. Iron is +2 oxidation state. What is the general configuration of iron? D6S2. Now, out of 2 electrons are out, D6. D6 configuration we are going to discuss in low spin complex. Here also iron is in +2 oxidation state. So, Fe +2. Again D6 in high spin complex. So, weak field and strong field we are going to discuss the CFSE calculation. So, what is the CFSE formula? Just now we have seen CFSE formula is equal to E from ligands minus E from the spectroscopic series, right? That is what we have seen it, right? We can see it from here. E from ligand field and E from isotropic field. E from ligand field and E from isotropic field. And now I am going to calculate CFSE. How to calculate CFSE? First, let me write the splitting. So what happens? First I have to fill 3 electrons, isn't it? First I have to fill 3 electrons. How to fill 3 electrons? 1, 2, 3. Next, third, fourth electron already we have a discussion. Fourth electron supposed to enter here or here? Supposed to enter here or here based on low spin complex. It is going to enter here only. Fifth electron here only. Sixth electron here only. What is called? This is called T2Z. This is called EZ. Right? This T2Z have how many electrons now? T2Z have how many electrons? T2Z have 6 electrons. So general configuration we will write it like this. T2Z EZ0. T2Z 6 electrons and EZ 0 electrons. Now how to calculate CFSE I am going to show you. So for calculation of CFSE we have a formula for octahedral. For octahedral we have a formula. The CFSE is equal to minus 0.4 into how many electrons of TZ are there? That M. M is electrons in the TZ. T2Z plus 0.6 into N into EZ. N is the number of electrons present in the EZ level. This one will come under delta naught. Right? And plus how many electrons are paired here? 1, 2, 3. 3 paired here. Right? This is completely going to be the energy for ligand. Energy from the ligand minus 0.4 M2DC 0.6 N2DC NEZ delta naught plus 3p. Now obviously from isotropic field how much? Isotropic means what is the meaning of isotropic we will discuss actually. Now so moving on to here minus isotropic. Here let us calculate CFSE for this particular one. CFSE how much? Minus 0.4. How many electrons are there in T2Z? 6. 6 T2Z plus 0.6 into how many electrons are there in EZ? 0 delta naught plus 3p coming after pairing, right? After this one 3p. Now what is isotropic means? What is the meaning of isotropic? It's going to be isotropic means what? Isotropic field means before this at degenerate level. At degenerate level, what is the 1, 2, 3, 4, 1, 2, 3, 4, 5, 6. So from isotropic means what is the meaning? This electron is there, right? This electron paired. So this is a paired, and so from isotropic field we are going to consider this one pair. At degenerate level, how many pairs are there? That many pairs we are going to consider in isotropic field. After splitting, how many pairs are there? That we are going to consider here, right? Now isotropic field, how many pairs will come? One pair minus one pair, right? So now minus 4 into 0.4 into 6 minus 2.4 delta naught plus 3p minus 2p, 3p minus 1p, 2p. So overall it is going to be minus 2 minus point minus 2.4 delta naught plus 2p. So this is for the CFSE for the octahedral complex of the D6 in strong field. Same way let us discuss in the weak field. D6 in weak field. How to first at degenerate level what happens? At degenerate level it is going to be 1, 2, 3, 4, 5, 6. Now at is going to be undergoing splitting, right? EZ and T2Z. How to fill electrons? 1, 2, 1, 2, 3. And fourth electron will enter into the higher energy level. 5, 4, 5. And sixth electron is here. Right? Here, if you are understanding here, right? Here, this is at degenerate level. At degenerate level. This is after splitting. Right? What is of CFSC formula? CFSC is equal to E ligand minus E isotropic field. Isotropic means what I told you? Isotropic means at degenerate level. How many pairs are there at degenerate level? Already one pair. One pair. Right? This is from isotropic level. Now from E ligand, I already told you this is going to be minus 0.4 m T2Z plus 0.6 n EZ delta naught plus how many pairs are there now? Here one pair. One pair. This complete this E ligand will come into this formula, right? And this is going to be CFSC. So minus 0.4 into how many TTGs are there now? 1, 2, 3, 4 electrons are there. 4, right? And then plus 0.6 into how many EGs are there now? 2. Delta naught. How many pairs are there after this one? It's going to be 1p minus 1p. Here if you are considering minus 1.6 plus 1.2 delta naught plus pp will get cancelled, and here if you are considering here, right, minus 0.4 delta naught. Already we know that delta naught is equal to 10 d cube, right? And if you want to convert this one into dq, right, this will become 4dq. Here what we have to observe very clearly, there will not be any pairing energy in the high field complex. High field complex, in a high field complex, there will not be any pairing energy topic. There will not be any letter called P. Why? Because before at the degenerate level and after splitting also it's going to have same type of P pairing, and so pairing energy will get cancelled. In the case of, if you are looking at here, right, in the case of, you can see here pairing energy is there. Why? Because pairing energy will come as it is low spin complex. In the high spin complex, the pairing energy will not be there. That's what the point we have to be noted here. And moving on to the topic, now let us calculate the CFSC from D1, D2, D3 to all the complexes for high spin and low spin complex also.